Hi, welcome to Topic 10. In Topic 10.1, it's really an introduction to organic chemistry and some of the basic ideas that you need to master to understand what's going on in organic chemistry. So first of all, what is organic chemistry? It's a big branch of chemistry. What we've been doing so far is considered inorganic chemistry, but organic chemistry is defined as any compound that contains carbon. And then besides carbon, it almost always contains hydrogen, and then often also oxygen, nitrogen, chlorine, and sulfur. And organic chemistry makes up all biological molecules. Anything living is going to be organic. It also can include non-living things such as synthetic materials, paints, detergents, refrigerants, fossil fuels, or it would also include formerly living or what we consider dead things. Carbon forms more compounds than all of the other elements form put together. So if you look at all the non-carbon based compounds out there compared to carbon based compounds, carbon would be the winner. Homologous series is kind of a name for organic families because carbon organic compounds are ubiquitous, meaning they're just everywhere because they make up so many things. They use a classification system all their own, so their families are called homologous series. And there's 5 things that are true about any homologous series, and that is, first of all, they all contain the same functional group, and we'll talk about that in a little bit. But like for alcohols, we've seen a lot, the functional group for alcohols is OH or hydroxy. They also can be represented by the same general formula. Successive members have an additional CH2. And we'll look at that. You just make what we call the backbone longer. The carbon chain just gets one longer. You put another carbon in the middle. It's attached to a carbon on each side and then 2 hydrogen on it. Members show a gradation in physical properties. Gradation just means an increase or a change. So boiling point density and viscosity are all going to increase as your members get bigger. And then they have similar chemical properties, which is why we consider them a family, because there's some similarities in them. So homologous series, kind of the big thing to understand is this idea of a carbon backbone and then the stuff that can be attached to that backbone. And this is really the root of what organic chemistry is being able to look at the structure and identify the backbone and identify either the functional groups or side chains attached to that backbone. So the backbone is the longest continuous connection of carbon atoms, and whether it's drawn as being, zigzag and kinked in there, doesn't matter. What you want to look at is how many carbons are directly bonded one to the other with no branching. And there's a couple ways to do that. You can look at how many CH3 groups are on there, because that'll let you know where there's branches or ends. I like to use my pencil and just see how many carbons can I touch without having to lift my pencil up. But so the hydrocarbon skeleton of the backbone is what helps you determine the root or stem name. And as the backbone grows, so does its effect on the characteristics of that particular molecule. It allows more temporary dipoles to form between molecules, or more van der Waals, which is going to tend to increase your density, increase your viscosity, and increase your boiling point as the intermolecular forces take on a bigger role. It also affects polarity, and this can be a good or a bad thing. The carbon backbone is going to be nonpolar. So if the functional group is also nonpolar, then you've got a really big nonpolar molecule. But it's more of an issue when the functional group is polar, like either OH or a double bonded O, because then that end is now polar, and then the nonpolar end you can think of as becoming like dead weight as far as how well it's going to interact with other polar substances such as water. So if you have a polar functional group, then shorter molecules are actually more polar or interact better with water and other polar substances, because a bigger percentage of the molecule is on that polar end, and there's less of the nonpolar end hanging on and having to be tagged along with your polar end. Empirical versus molecular formula, we've been through this a couple times, but again, even in organic chemistry, you can determine empirical and molecular formulas. And you do it the same way. You have to find out the molar amounts of each. So I've got a quick example built into the notes here that we'll look at on the next page here. So information given is that a glucose is composed of 40% carbon, 53.3% oxygen, and 6.7% hydrogen. You got a relative mass. So what are the empirical and molecular formulas? So if I start with my 40% carbon and divide that by the 1201 grams per mole, I see that I've got 3.33 moles of carbon. And then if I take my 53.3 grams or percent of oxygen and divide by the 16 grams per mole, that also gives me 3.33 moles of oxygen. And then my hydrogen, I've got 6.70. Divide that by the 101, and this is going to give me like 6.69, I think it is, moles of hydrogen. And let me just pause a minute here and slide this down. Okay, so looking at our molar amounts then, to set up my ratio, I need to divide these each by the smallest molar amount and see what my ratios work out to be. And so C and O are going to be 1 each, and then the H is going to be like 1.99, so with sig figs we could round it to 2, so COH2. And then to finish up, I have to remember that I was given an experimental molar mass of 180 maybe 02, 180 I guess, and so I have to determine what would be the molar mass if this were, if the empirical formula were the actual formula. And if I do that, I come up with 12.01 plus 16 plus the 202. So this is 30.03. And when I divide this, this is 5.99. So I see that this is 6 times heavier, which means this then also is going to be 6 times everything in there. C6O6. H12 would be my molecular formula. So that's a quick review of empirical and molecular formulas. So moving on as I clear this and get to our next screen, 2 really common homologous series that 10.1 focuses on are the alkanes and alcohols. And I've just listed some of the common alkanes that you've maybe heard of: methane, ethane, propane, butane, and octane. Those are ones that we use commonly in our day-to-day lives. Technically, they don't contain a functional group. I think of their functional group as just being another hydrogen, because that's all it is carbon and hydrogen. All single bonds. So the functional group is, again, just hydrogen or no functional group, and it's represented by the formula CN H2N plus 2. So if you were asked to write the formula for the first 4 alkanes and draw the condensed, or write the condensed structural formulas, let me show you what's meant by that. So let me just keep the formula there for you. And so the first one would be C1, or just C, and then H would be 2 times 1 plus 2, or CH4. Now, let me erase that and see if I can get a little clearer for you. So CH4, and that would also be the condensed structural formula, because that's all there is to it. And so drawing it would just be C with the 4 H's attached to it. And then the second one would be C2. And now H is going to go up to 2 times 2 is 4 is 6. So then my condensed structural formula would be CH3, CH3. And now when I draw this, I'd have 2 carbons single bonded and then filled in with hydrogens. And these are called saturated hydrocarbons because the carbon is saturated with single bonds. Each carbon has 4 single bonds on it. And then if I clear this and look at the last 2, so that's methane and ethane are their names because they have 1 and 2 carbons. Propane is the third one, so it'd be C3, and then H would be 6 plus 2 would be C3H8. So this would be CH3, CH2, CH3, and it maybe it's easier to draw these first before you can see the structural formula, but the idea is at some point you can write the condensed structural formula without having to draw it. That's the whole purpose, is that you don't have to draw these big long structures to be able to come up with that condensed formula. And then finally, butane is C4H10. And you can see that each time I'm adding another carbon, you always have two ends regardless of how short your chain is, unless of course it's methanol, or methane I should say. So you can see how each time I am indeed just adding a CH2 group as I make this longer and longer, but the basic formula remains the same. And just a couple hints down here that I want to touch on before I go to the next screen is that there's 3 tables in your book that give you a lot of information. You're expected to memorize the functional groups for 5 different families, but you really don't have to, because the tables in your booklet will give you names and formulas, and you'll be able to reason it out from there. So you have to be able to reason it out, but you don't have to flat out memorize this stuff. Okay, so then alcohols, the other family they talk about in 10.1 is represented with the functional group OH, or it's called a hydroxy group because it's really a hydroxide. They're represented by the formula CnH2n plus 1 OH. And it says write the formulas for the first 4 alcohols, then write the condensed structural formulas and draw the structures. So again, let me scroll this down a little bit and we'll take a look at this. So my first one, C1, H is 2 times 1 plus 1 is going to be CH3, OH. And my condensed structural formula is going to be the same again. And so when I draw this, I'm going to have 3 hydrogens. And in place of that 4th hydrogen is going to be the OH group. So then when I write the second one, C2, now H has gone up to 5 OH, and that means that I have a CH3 group on the end, and then I have a CH2 group, and instead of another hydrogen, there'd be an OH group. So now when I draw this, this would be CC, the OH group. It doesn't really matter if I put it off to the end or if I put it on the top or bottom, because it's just a matter of which way you have it rotated. You could think of it as being in any of those positions. But that's my first 2. And then we'll come back to the naming, but these would, instead of being called methane and ethane, now we'd call them methanol and ethanol to show that they have the alcohol functional group on them. Now let me clear this and then look at ethanol and butanol. Ethanol is going to have 3 carbons, so C3, and then it's going to be H7, OH. So I'm going to have a CH3 group, a CH2 group, and then a CH2 group with that OH on it. So when I draw this, it would look like this. And then my butanol, C4, H9, OH. It's going to look very similar. 1, 2, 3, 4. My OH here. Fill in my H's. And my condensed structural formula for this is CH3, CH2, CH2, and then CH2OH, and I actually could shorten that up to CH3, CH23OH. And either of those is fine, whatever makes more sense to you. The one thing I want to mention is, does the OH have to be on the end here? And the answer is no. We're going to look next at what are called isomers or structural isomers. This OH that's right here could just as easily be off the middle carbon. It could be on the other end, but then, see I missed a hydrogen there. If it was on the other end, it would just be a matter of flipping this over, so it won't look any different. And this OH group could just as easily be on the second carbon in from either end. And in fact, this carbon, this butane group, wouldn't have to have all 3 carbons in the row. One of these carbons could be branched off the center. So we start getting into, as we hit 3 and 4, ethanol and butanol for alcohol, we start hitting this possibility of being able to draw the structure more